In this next tutorial, we will solve more complex exponential and logarithmic equations and be sure to check for extraneous solutions. So let's flip over to example 4 and we'll start looking at complex exponential and logarithmic equations. We have a few steps to follow and I'd like to go through these 3 steps while working through example number 4. So the first step and the most important before we can do anything, we must isolate the base. Isolate means to get the base all by itself, nothing else next to it. So what we need to do is identify what the base is, and of course the base is the thing that's being raised to an exponent, so the base is e. The base is not 4e. If we wanted the base to be 4e, we would have to have parentheses around that expression 4e. So it's not. The base is just e. So to isolate that, I need to get rid of the 5, and I need to get rid of this coefficient of 4. So let's subtract 5 first. 4e to the x. Subtract 5, we've got 56. And then we'll divide the 4 away, since it's just a coefficient. And I'll have e to the x is equal to 14. So we've isolated the base. It has to be all by itself. The next step, we have a bunch of options, really. We could take the common log of both sides. We could take the natural log of both sides. Or if we have some random base that's not base 10 or base e, we could take the log base, whatever that number is, of both sides. There's actually another thing I'll show you on one of the other examples, but it doesn't always work, so I'll just show you on that one. In this case, since we're talking about base e, of course it makes sense to use the natural log. So I'm going to take the natural log of both sides. I'm going to take the natural log of the left side, so natural log of e to the x, and I'm going to say that that's equal to the natural log of 14. This is a fine step to do in an equation. It's sort of like adding 5 to both sides. We can do that. I'm going to take the natural log of both sides. Now I chose to take the natural log because we know that the natural log of e to the x just basically cancels out to become x. If you don't remember, you remember there's a little base e that's hiding right here. You know that it's there, and e would have to be raised to the x power to become e to the x power. Or we could use one of the properties that says if I have a logarithm with an exponent inside, I can bring the exponent outside and make this x right here, and then times the natural log of e. But the natural log of e is 1, so it would be x times 1. Any way you think about this, it will just equal x, and x will be equal to the natural log of 14. Whatever that is, I'm going to use my calculator, and that's our step 3. It says use your calculator to approximate your solutions. Plug it into the calc, and let's go to at least 3 decimal places. So I'll plug into the calc the natural log of 14, and I'm coming over here, use the natural log button, 14. It's good to close parentheses, and we'll press enter, and I get 2.639. And that's exactly what it would be rounded to 3 decimal places, 2.639. And that's it. We solved our first one. We don't have to worry about extraneous solutions when we're talking about exponential. If you remember the graphs of exponential, this is what a basic graph looks like. The domain is everything. X can be anything, so any number is probably going to, well, not any number works, this number works. It's the only number that works. What I'm saying is that X can be any number. Okay, so let's look at those same steps and let's look at example 5. Example 5 is not a simple exponential equation like we looked at in the first tutorial. I see a base 2, but there's no way to rewrite 20 using base 2. The base 2's would be something like 8, 4, 8, 16, 32, so 20 is no good. I need to isolate the base, that's what step 1 says, and this base is already isolated. So now I could take the common log of both sides, or the natural log of both sides, or the log base, in this case, the log base 2 of both sides. Let me show you 3 different ways to solve this equation. Let's first start by taking the common log of both sides. I'm going to take the common log of this left side, and the common log of this right side. Okay, now that I have a logarithm, I can use my properties, and one of my properties says that if I have an exponent inside, I can bring that exponent right outside, and I've got x times the log of 2 is equal to the log of 20. And if I'm just solving for x, now I can just divide whatever this log of 2 number is. I don't know what it is, but it is just a number, and I can divide both sides by that, and I'll have x is equal to this, the log of 20 divided by the log of 2. And I can plug that into the calculator. Or, let me show you another way. Instead of taking the common log of both sides, since I'm dealing with base 2, how about I take the log base 2 of both sides? So log base 2 of 2 to the x and the log base 2 of 20. It's the log base 2 of both sides. Do you see what's happening here? The log base 2 kind of cancels out this base 2, and we're just left with x. And x would be equal to the log base 2 of 20. And we know that the change of base formula says that the log base 2 of 20 is equal to the common log of the number 20 divided by the common log of the base 2. So we know that these two things will be the same, and we can plug that into the calculator. One last way, and this really only works for something that looks like this. If we have 2 to the x is equal to 20, we could use our idea of rewriting this exponential equation and put it into logarithmic form. We'd write the log, the base is 2, the number is 20, and that must be equal to the exponent x. And that, of course, is the same exact thing that we just wrote right here in the purple. So there are 3 different ways to solve this. And let's just make sure that these work, of course. The log of 20 divided by the log of 2 is what we had first. So we'll do the log of 20. Make sure you close that parenthesis before you hit the division. The log of 2, and we'll close that parenthesis. That gives me 4.322 if I round to 3 decimal places. The other way, if I have the log base 2 of 20, I can just go to my math. I'm going to press up twice to get to it. It's a little bit faster. The log base, and use that change of base idea, but the calculator has a little spot for the base, which is 2, and for the number in this case is 20. So I can just plug that into the calc, and of course I get the same thing, 4.322. So that's what x is. And I'll just do that right in here. 4.322. So either the first two are nice options, I think. This third one really only works when there's a variable only on one side of the equation. So that, of course, is not going to work here for example 6. I have a variable on both sides. So what I really need to do, actually, I can't even do the little trick where I can use the log base whatever because I have 2 different bases. So the only way to attack this problem really is to take the common log of both sides. I'm going to take the common log of 5 to the 3x plus 2 and set that equal to the common log of 30 to the x. This is really the only way to go here. That affords me the opportunity to bring this exponent outside. Since it's a binomial, I'm going to keep it in parentheses times the common log of 5. And this one will just come right on outside, x times the common log of 30. What's nice about this step is that now there are no exponents really. The x's are now just, regular terms that I can solve, algebraically. I do have a set of parentheses that need to be unlocked, so I'm going to distribute this number. I don't know what the log of 5 is, but it is just a number. So I'll do 3x times the log of 5. Plus 2 times the log of 5. I'm just distributing. And that's equal to this x log of 30. So now I've got a situation where I'm trying to find x, and x is here in this term and also in this term. I have 3 total terms in my equation. 2 of them have my variable. When we have a situation like this, what we've seen or what we've done before is we've taken these 2 terms, or all the terms that have the variable, and put them on one side of the equal sign, and put the other thing on the other side of the equal sign. So I'm going to subtract this term and make it join over here. Now I'm going to kind of put it here in the middle because it's not really like terms with this one. I'm not going to be able to combine them, or at least I'm not going to combine them. And at the same time, I'm going to subtract this term, this 2 log of 5, subtract that over to here. And let's see what happens. So I've got these two terms. They're not like terms, so I'm just going to write them side by side. 3x log of 5 minus x log of 30 is equal to, this is over here, negative 2 log of 5. So again, what I just did is I put the two terms that have my variable on one side and anything else on the other side. What I can do now is pull that x out, like a GCF. I'm going to factor this x out. What's left from this first term would be the 3 in the log of 5. What's left from the second term is the log of 30. And of course, nothing changes over here. What's nice now is I just have that 1x. All I need to do is get rid of this number, whatever that number is. The calculator will figure it out. I'm just going to divide that number away, the 3 log of 5 minus log of 30, and I'll divide that to both sides. Because this number, whatever it is, divided by itself, whoosh, cancels away. X will be all by itself. I need to plug this into the calculator. Of course, when we get here, we've done all this work. We want to make sure that we speak to the calculator correctly. Might as well put parentheses around the entire numerator and around the entire denominator. Now understand, whenever you push the log button, it opens up a set of parentheses that needs to be closed. And we need to put surrounding parentheses around all of that. So let's see if we can plug this into the calculator. We would not like to get all this way and not be able to speak to the calculator. So I've got parentheses. I'm putting the negative 2 log of 5. Now notice that I have to close the parentheses for the 5, or for the logarithm, and then close the parentheses for that numerator. Now I'm going to divide by a new set of parentheses. I've got 3 log of 5. I have to close that first parenthesis. Or that, not the first one, but the the logarithm one, minus the log of 30. Close that second log parenthesis, and then the main one of the denominator. That should be it. Let's see what we've got. Negative 2.256. Remember, if we're rounding to 3 decimal places, we go to the third decimal place, and if the number to the right of it is 5 or more, then that number goes up. So negative 2.256. Negative 2.256. And we've got our solution. Let's look at example 7. So this time we have a logarithmic equation. We have 2 times the natural log of 3x is equal to 4. So we have to watch out for this, since we're talking about a logarithmic equation. And if you remember, I'm just going to draw a quick graph of that. A logarithmic function generally looks like that, where we have that vertical asymptote. This time we have a restricted domain. Maybe I just dot that in there. We have a restricted domain. Only positives can be right here. So I know that x cannot be a negative number. In fact, x can't be 0 either, because we can't even have 0 be here. We cannot be on that vertical asymptote. So we have to watch out for, this is where we might have extraneous solutions. So I'm still trying to find x. And, a rule of thumb when I'm solving an equation is the number that's closest to x is usually the last number to go away. So that 3 is going to be my last move. The next thing, which is this natural log, that's the next thing to go away. And the number that's farthest away from my variable is usually the first thing to go away. Now, some people might say, you know what, why don't we bring this 2 inside and make it a squared thing? But I'd prefer not to deal with the quadratic if I don't have to. This really is just a 2 that I can just divide away. I can divide that to both sides. So I'll have the natural log of 3x is equal to 4 divided by 2 is 2. So now we're trying to figure out what this answer is. And this logarithmic form doesn't really help me. So what I'm going to do is I'm going to rewrite. I'm going to convert. We practiced plenty of times converting out of logarithmic and into exponential. I do need to know what the base is, and we know that there's a little e hiding here. So I'm going to say that the base e raised to the second power is equal to this number 3x. That's just a simple conversion. And that's a whole lot easier to solve, I think. Now to solve for x, all we have to do is divide by 3. And I'll have x is equal to whatever squared, whatever e squared divided by 3 is. So I'll plug that into the calculator and I'll get my approximation. So let's see what we have. E, if you don't already know, is hiding above the division button on this calculator. So I can say second E, and I'll raise that to the second power. And then I'll take that whole thing and divide by 3. So there's my 2.463. 2.463. So that's not too bad. Oh, and I know that I can circle this because this is a positive number. Remember, we can only plug positive numbers into here, and that makes sense. Let's look at our 8th example. So this is interesting. This is the first time we've actually seen two terms that have our base. And there's no way, because we have this third term, and that's kind of not too good, there's no way to put each term on either side and like take the natural log of both sides. We can't really do that. This is where we're going to be factoring. And I'm going to show you how to factor this one. And the key is understanding really what this e to the 2x represents. That really is e to the x squared. And that's kind of the key to this one. Understand that when we have e to the x squared, we're multiplying the exponents. That's why it was 2x, or it is 2x. But if I write it as e to the x squared minus 3 e to the x plus 2 is equal to 0, this basically follows a quadratic pattern. The quadratic pattern is a squared, something squared, minus 3 of those same somethings plus 2 is equal to 0. This is a quadratic that I know how to factor. So since I know that that's going to factor, I'm going to go ahead and put my parentheses. I'm not going to forget that, of course, it's equal to 0. E to the x squared splits up into e to the x times e to the x, just like a squared would split up into a times a. The back of the parentheses, well, there's only one way to multiply to get 2. It's a 1 and a 2, so I'll go ahead and put those in there. And, whoops, excuse me. And I know since that's a positive 2, I have to either multiply a positive times a positive or a negative times a negative. And since that middle term has a negative, I know that it's negative times negative. So that's how I factored that. And if you have trouble factoring with this, understand that it's the same thing as, a squared minus 3a plus 2. Go ahead and factor this and then just replace the a with an e to the x. So now I have this factor where e to the x minus 1 is equal to 0, and I have this factor where e to the x minus 2 is equal to 0. Solving each of these, I have e to the x is equal to positive 1, or I have e to the x is equal to positive 2. Well, this one hopefully is not too difficult to solve. Hopefully you know that x has to be 0. You could use your calculator if you need to check that, but anything to the 0 is equal to 1. So that's one of our answers. This one, I don't know what e has to be raised to get 2. So in this case, I'm going to do one of my techniques. I can either convert it into logarithmic form, or I could take the natural log of both sides, which is what I'm going to be doing. The natural log of e to the x equals the natural log of 2. Remember, doing that simply makes the natural log of e go away, and I get x is equal to the natural log of 2. And then I can plug that into the calculator and get my second answer. Get my calc up. I've got natural log of 2. Close the parenthesis. 0.693. So 0.693. So this one has two solutions, 0 and 0.693. And it has two solutions because it was following a quadratic pattern, and there's normally two solutions to a quadratic. Excellent. We do have one final example, example 9, another logarithmic equation. So we have to watch out for our domain. We've got the natural log of x minus 2 plus the natural log of 2x minus 3 is equal to 2 natural log of x. So what are we going to do here? We've got these two terms, and I know that there's a property that says that I can join them together into a single log. We were just looking at the logarithmic properties. So if I have a log plus another log, I can condense them together And since there's a plus sign there, I know that what I'm going to be doing is taking those two numbers and multiplying them. So the x minus 2 and the 2x minus 3 are going to become a product. That's how I can condense these into a single logarithm. And that, of course, will be equal to this, 2 natural log of x. So now perhaps I would FOIL this. And x times 2x, of course, is 2x squared. The outer terms are negative 3x. The inner terms are negative 4x. That makes negative 7x. The last terms multiply to give positive 6. And I might do something over here. This 2 probably shouldn't be over here. It should probably come inside and make a little x squared. I know in a previous problem I divided that 2, but that wouldn't do me any good over here because then I would just have some sort of denominator over here, and I don't like that. So I'll just bring it in and make it an x squared. So I have this logarithm equal this logarithm. And since they have the same bases, I know that this expression must be the same thing as this expression. So it's like the logarithms are kind of irrelevant at this point. I just need to know that the 2x squared minus 7x plus 6 is equal to the x squared. The logarithms, they don't divide away. They don't divide away. They just become irrelevant. So this expression has to equal this expression. And then I have this equation. Well, that's fun because that's just an algebra 2 equation. It's really just an algebra 1. It's quadratic, so I probably need to set it equal to 0. I'm going to subtract the x squared from its like term over here. And I've got x squared minus 7x plus 6 is equal to 0. And this looks like something that will factor. So I'll go ahead and factor this. I will not forget my equation. X times x is the only way to get x squared. I've got 1 times 6, but I also have 2 times 3. So I'm looking at this middle number of 7, and that's a dead giveaway that it's probably going to be the 1 and the 6. I know that both my signs need to be the same. This time they also need to both be negative. So it looks like I have my two solutions. This factor is going to give me x equals 1, and this factor is going to give me x equals 6. And you'd think we'd be finished. But why am I showing you this one? We must check for extraneous solutions. When we're dealing with logarithmic equations, we can't just plug everything in. This expression, this number, the log of the thing has to be positive, has to stay positive. Same with this one. Same with this one. So if I plug a 6 into this expression, I'm going to have 6 minus 2. Well, that's nice because that stays positive. If I plug a 6 here, I get 12 minus 3, which is 9. That's nice because that stays positive. If I plug a 6 here, of course, 6 is positive, so there we go. So 6 is a fine solution. But what happens when I plug in a 1? If I plug a 1 into here, 1 minus 2, that's no good. We don't have the natural log of a negative number. This is an extraneous solution. So please be sure to check, especially when you're dealing with logarithmic equations. Thanks for watching this tutorial. I know we looked at 9 good examples, 6 of them in this tutorial alone. Please go back and review each of those, and I'll see you in class for some practice. See ya.